This is Frau Blücher, a mobile robot designed by Basia, Gabriel, and Adrien as part of the EC492 Capstone Design course at the University of Alberta. The project was sponsored and supervised by the client Dr. Stephen Knudsen. The goal of the project was to build a modular battery-powered robot using repurposed parts from previous student projects. Inspired by the idea of a robotic lab companion, Frau Blücher was designed to autonomously navigate the EC492 lab space, track a signal from a user-operated beacon, and avoid obstacles in real time. The system is divided into two subsystems, a beacon held by the user and the robot, which uses Bluetooth for signal tracking and LiDAR for obstacle detection. Despite some setbacks, including switching from RF to Bluetooth due to communication issues, the final prototype met nearly all of its functional goals. It reliably moves towards the beacon, avoids obstacles, and runs on battery power for over 30 minutes. The result is a low-cost, adaptable robot that can showcase both practical design and creative reuse.
For the locomotion system, we chose to use low-power DC motors paired with tracks that were found in the lab. Since the robot is not required to move at high speeds, the DC motors are more than enough. They also have the benefit of requiring little power, which allows the robot to run for far longer without depleting the batteries. The use of tracks allow for easy directional control while simplifying the design. Unlike a four-wheel design like in cars, tracks only require two motors to operate. They also allowed the robot to make turns while remaining stationary, which is helpful when implementing object avoidance. To drive the motors, we selected a spark front motor driver, which was also already present in the lab. It fit our design perfectly as it is capable of simultaneously driving two motors with inputs from a controller. The only issue we ran into for this system was the synchronization of the motors. Early into the implementation, we realized that the motors were spinning at different speeds, which made the robot turn even when trying to go straight. To fix this, we had to adjust the motor's power individually to make their performance more even. To make the robot reach a destination, we first needed to find a way to identify said destination, so we decided to use a beacon and probe approach. The robot itself acts as a probe and looks for a signal that the beacon is continuously sending. To implement this, we decided to use Bluetooth. Both the beacon and the robot are equipped with a Raspberry Pi Pico W, which has an onboard wireless interface that supports Bluetooth. Since the Pico comes with the onboard interface, it means we don't have to use extra components that might introduce more errors. Once turned on, the beacon's Pico starts to send signals to the robot, and the robot starts moving until it reaches the beacon. Since Bluetooth is omnidirectional, we use the signal strength to know if the robot is heading in the right direction. Every few moments, the robot will measure the average signal strength and compare it to a previous measured average signal strength. If the signal has gotten stronger, the robot will continue to move forward, but if it decreased, the robot will take a 90-degree turn and advance in a new direction. Once the signal reaches a certain threshold, the robot considers the destination reached and stops moving. Although this ensures that the robot will not stop until it reaches the beacon, it comes with a drawback. If the robot is not moving directly towards or away from the beacon, it will require significant movement before realizing that it needs to adjust.
One of the key components we used for navigation was the LiDAR Light V2, a sensor that measures distance using laser pulses. We used this to detect obstacles within 30 centimeters in front of the robot so it could turn when something was in its path. Initially, we tried to connect the LiDAR using I2C communication, but despite following the documentation closely and testing different configurations, we just couldn't get stable readings. The sensor either wouldn't respond or it gave inconsistent values. Eventually, we switched the LiDAR to PWM mode, which worked much better with our Raspberry Pi Pico W. In PWM mode, the LiDAR sends a pulse signal that represents distance, and the Pico reads that length of the pulse to determine how far an object is. This simplified the setup and removed a lot of the connection issues we had before. Even with PWM working, tuning the threshold for when the robot should turn versus when it should keep moving took some trial and error, but in the end, the LiDAR successfully helped the robot avoid walls and obstacles, which was a crucial part of our autonomous behavior.
For proper feedback and easier debugging, we connected a LED wing to the Pico. This allowed us to assign a color to each state of the robot. This meant that the destination reached, moving and avoiding obstacle states now displayed a blue, green, and red color respectively. We implemented this in Frau Blücher's software using the NeoPixel library. We originally planned on adding blinking lights and patterns, but the timing of the lights interfered too much with the real-time system of the robot. We also had trouble when connecting the pins of the LED wings, since one of them broke off during usage. A workaround was to use instead the pins of a random LED to supply the entire wing.
For this demo, we have the robot and the beacon in an obstacle course. Once the beacon is on, for the robot to reach it, it will first have to avoid this panel and this one. To get it started, after connecting the robot to the power supply like this, all we have to do is turn on the switch to activate the peripherals, notably the LiDAR and the lights. Then, all we have to do is turn on the beacon. The robot immediately starts moving, but then turns right when it detects the first panel. It then continues to go forward. After it detects the second panel, it starts switching again. After avoiding all the panels, it continues to go straight and will continue to do so until it gets a strong enough signal from the beacon, like so, and it will stop.
While the current Franken-Bot meets its design goals, there are still improvements to be made. A potential upgrade would be to replace the Bluetooth system of Frau Blücher with a proper radio frequency system. This would give the robot a sense of direction and would achieve more reliable and powerful signal transmission. Another improvement would be to upgrade localization by installing a multi-beacon setup. Each beacon would be placed in a fixed position in a triangular configuration, helping the robot estimate its position. This would remove the need for constant rotational scanning and give more responsive navigation. Adding a manual override system, such as a reused RC controller or mobile interface, was also considered. It would allow users to directly control Frau Blücher when needed, especially in scenarios where the robot encounters unexpected obstacles or fails to detect a signal. There was also interest in making Frau Blücher memorize and store previous paths, and use that information to make smarter navigation decisions in previously explored environments. Even a simple path recall would improve usefulness in structured spaces like laboratories or classrooms. Finally, improving the modularity of both software and hardware will make future upgrades much more seamless. Such a flexible design will support quick integration of new components, allowing more versatility for experimentation and learning.
To wrap things up, Frau Blücher achieved what we set out to do, a modular mobile robot that could move toward a beacon and avoid obstacles, all using recycled hardware. We reused parts like motors, tracks, and a SparkFun motor driver, and made key decisions around availability, simplicity, and cost. While the Bluetooth signal tracking wasn't as precise as we hoped, since it's not directional, it still allowed us to demonstrate autonomous movement and real-time response to the user's location. The LiDAR obstacle avoidance worked well, and the robot was able to run for over 30 minutes, meeting one of our core performance goals. The prototype leaves room for future upgrades, including a proper RF system, a manual control mode, and path memory. But overall, this was a great learning experience in hardware reuse, embedded systems, and hands-on robotic design.